Let's now try and understand potential energy. Gravitational potential energy del U. Now where G is gravitational constant and M is mass of Earth, small m is any other mass, could be a satellite, and Ri is initial distance where the mass or the satellite is, and Rf is the final distance. So Ri is initial position of object and Rf is final position of object. So this is the formula. We substitute in this formula and we can get in gravitational potential energy. Alright, now when we talk about potential energy on the surface of the Earth, this formula is applicable when we intend to detect gravitational potential energy when an object is moving either from surface of the Earth or closer to surface of the Earth to further away, or from further away to closer to surface of Earth. So this is the formula that we use. Now potential energy on the surface of the Earth is minus gmm upon r, which we designated by u1 say, and potential energy at height is minus gmm upon r plus h, where r is obviously radius of Earth and height is the height at which the object is. We call it as u2. So increase in potential or change in potential energy would be u2 minus u1, which on subtracting would be gmmh upon r into r plus h. Now we also know gm is equal to gr square. This is gravitational constant and this is acceleration due to gravity. M is mass of Earth and r is radius of Earth. Now this, how do we get it? See, force mg is equal to force gmm upon r square, gravitational force. When we equilibrate it, force mg is equivalent to gravitational force, which is gmm upon r square. So what we get is, if we cancel mass and mass of Earth stays and r square goes there, so gm is equal to gr square. So this is what we are going to apply in many places. So here, for example, so here we already had gm mh upon r bracket r plus h. So we can, instead of this, we can substitute it as gr square, and on substitution of gr square, 1r cancels. So our final formula in terms of acceleration due to gravity is mgh r upon r plus h. My main contention of this video is to keep you abreast with the formulae that we may be using in our JEE and NEET program. Alright. Next that we see is gravitational potential. Gravitational potential. Potential energy, gravitational. Gravitational potential into mass is gravitational potential energy. Alright. So minus gm upon r into m. So the formula for gravitational potential energy is minus gmm upon r on the Earth's surface, or it can also be minus gmm upon small r, where small r is radius plus height at which the object is. So what we talked till now was about potential energy, gravitational potential energy. Now let's talk about gravitational potential. So gravitational potential would be gravitational potential energy per mass. Alright. So we take this formula or this formula, divide both the formula by mass, small mass, that is mass of object or mass of satellite, whatever it is. So ultimately what we end up with is gravitational potential formula being minus gm upon capital R, or it would be minus gm upon small r. Now the formula Gp is equal to minus gm upon r can also be derived this way. Gravitational potential is directly proportional to mass of Earth. Gravitational potential is inversely proportional to distance of object from Earth. Now in this case we have taken object to be on the surface of Earth, so r, radius of Earth. But if the object is away from surface of Earth, then this would be small r, which would be equal to capital R plus h, that is radius of Earth, plus h, the distance of object from surface of Earth, as we have been seeing. So if we eradicate proportionality sign, then what we end up is with a constant, which is gravitational constant, capital G. So our formula for gravitational potential is minus gm over r. Now the next mission is why minus. It is minus because it is negative because work is done against gravitational force for displacement. That's why this negative sign comes into picture. Value for gravitational constant is 6.67 into 10 raised to minus 11 Newton meter square per kg square. Now how do we get this unit? Let's try and understand. The formula for force we know is Gmm upon r square. Now since we are interested in finding unit for G, we put into denominator, we put this in the numerator, so we get this. Now unit for force is Newton, r square is meter square, and mass of Earth and mass of object both are kgs. We are dealing with SI unit, so kg, 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 kg. So unit gets the form of n m square upon kg square. Alright, so Newton meter square per kg square. That's the unit we get. So this is how we get the unit. Another thing that I need to bring to your notice is about mass. Mass of Earth specifically. We know Earth is a sphere. Alright. Now mass of Earth can also be replaced by 4 by 3 pi r cube rho, where rho is density. Density is mass over volume, and mass is mass, and volume we can put it as 4 by 3 pi r cube, as Earth resembles sphere. Alright. So now what do we do? Now want to get it in terms of mass and rho. So what I do is I take it there, multiply it with rho, so I get mass. Just neglect this for time being. Alright, so we take this there, the denominator is taken over here, multiplied with rho to get m. So m is equal to 4 by 3 pi r cube rho. Whenever we are tackling numericals, do not forget that instead of mass, we can also put in 4 by 3 pi r cube rho. Alright, for Earth. And again, it all depends, of course, whether the other object, which is that's also a sphere or not. Alright, so while tackling numericals, these are the things which we have got to take care of.